Right now, you are moving, not walking, not driving, spinning. At the equator, you are traveling east at about 1,670 kilometers per hour, and you feel none of it because everything around you is moving with you. But if, for just 1 second, Earth stopped, what would actually happen? Earth completes one rotation every 24 hours. That steady spin shapes almost every large-scale pattern on the planet. It determines the length of day and night. It influences wind directions. It helps organize ocean currents. It contributes to how storms rotate. At the equator, the surface moves fastest, about 465 meters per second, roughly the speed of a commercial jet. As you move toward the poles, that speed decreases. You do not notice this motion because the ground, the oceans, and the atmosphere are all rotating together at the same speed. The system works because everything shares the same motion. Earth's rotation is extremely stable. It changes slowly over millions of years, mainly because of tidal forces from the moon. The length of a day increases by only milliseconds per century. There is no known natural process that could suddenly stop the entire planet for 1 second and then restart it. So this scenario is not a prediction, it is a physics, thought, experiment. We are asking, if the solid Earth stopped for 1 second but the air and oceans kept moving due to inertia, what would follow? Let's define the scenario clearly. Earth's solid surface instantly stops rotating. It remains stopped for exactly 1 second. Then it instantly resumes spinning at its normal speed. Gravity, orbit, and tilt remain unchanged. The key idea is inertia. Inertia means that moving things tend to keep moving unless something stops them. If the ground suddenly stops, the atmosphere and oceans would not stop immediately. They would continue moving east at their original speeds, at least at first. That difference in motion is where the consequences begin. The first minutes. The most important number here is 465 meters per second. At the equator, if the ground stops but the air keeps moving, the surface would suddenly experience extremely powerful winds moving eastward. To visualize this, imagine standing still while a jet-speed wind passes over you. This is not ordinary weather. This is a sudden mismatch between the motion of the planet and the motion of the air. 3 major physical processes begin immediately. 1. Extreme surface winds and turbulence. The lowest layer of the atmosphere, called the boundary layer, is where air interacts directly with the ground. Normally, friction keeps air and surface motion closely linked. When the surface stops, that link breaks. The result would be violent turbulence. Air would rapidly slow down as it rubs against mountains, forests, cities, and oceans. That friction converts motion into heat, but mostly it produces chaotic wind and mechanical damage. 2. Ocean surface disruption. The oceans would continue moving eastward as well. Water has mass. It resists changes in motion, so the upper ocean would surge relative to the stationary ground beneath it. This would generate enormous wave energy and intense mixing near the surface. Coastal regions would be especially vulnerable because shallow waters amplify wave effects. 3. The Coriolis effect disappears briefly. Normally, Earth's rotation causes moving air to curve. This is called the Coriolis effect. It is why hurricanes rotate and why trade winds blow in specific directions. For 1 second, if rotation is 0, the Coriolis effect disappears. In 1 second, the atmosphere does not have time to reorganize globally. But during that second, the force balance that normally shapes wind patterns vanishes. Then, rotation resumes. The ground accelerates back eastward, beneath an atmosphere that has already begun slowing from friction. This creates another abrupt adjustment. The first hours. By this point, the initial shock has passed, but the system is far from stable. The main processes now are turbulence, settling energy, dissipating, particles being lifted into the air, ocean layers mixing. Large amounts of dust, sea salt, smoke, and debris would likely be suspended in the atmosphere. These tiny particles are called aerosols. Aerosols matter because they interact with sunlight. Some reflect sunlight back to space, some absorb heat, some help clouds form by acting as condensation seeds. The climate impact in the first hours depends heavily on how much material is lofted and how high it reaches. The ocean's upper layer, called the mixed layer, would also deepen in some regions due to strong wind and wave action. When deeper water mixes upward, it can cool the surface temporarily, bring nutrients upward, potentially feeding short-lived plankton blooms. But this response would vary widely by region. The first day's weather systems operate on timescales of days. By now, atmospheric circulation would be reorganizing from the disturbance. Because the rotation pause lasted only 1 second, global circulation patterns would not permanently change. However, the atmosphere would now be heavily disturbed and loaded with aerosols. Possible short-term outcomes: reduced sunlight at the surface in dusty regions, altered precipitation patterns, increased rainfall where aerosols enhance cloud formation. Coastal ecosystems would likely suffer the most. Sediment clouds reduce light for coral reefs and seagrass. Kelp forests could be torn apart. Estuaries would experience salinity and sediment shocks. In the first few weeks, ecological consequences would compound. Regarding forests, widespread wind throw, trees uprooted by extreme lateral forces, increases dead biomass. This raises fire risk in subsequent dry seasons. Topsoil erosion reduces productivity. Saltwater intrusion into coastal farmland damages crops. If nutrient upwelling fuels plankton blooms, decomposition may reduce oxygen in coastal waters, stressing fish populations. The climate signal at this stage depends less on rotation itself and more on how much biomass and infrastructure were lost. Long-term climate effects depend on secondary processes: carbon released from fires and ecosystem loss, land surface changes affecting reflectivity, albedo, persistent damage to coastal ecosystems, disruptions to food systems. Major ocean currents would likely recover because they are driven by sustained planetary rotation and temperature gradients, not by 1-second events. But ecosystems may not fully return to their previous state. Some regions could experience long-term shifts in vegetation, fisheries, or hydrology. Climate interacts with human systems. If coastlines are reshaped, agriculture shifts. If forests are lost, regional rainfall patterns can change. If fisheries collapse, food distribution systems are stressed. The physical disturbance would cascade into social systems. Even though this is a climate-focused exploration, human consequences would be unavoidable. Near the equator, the effective forces from a sudden stop could exceed 40 times Earth's gravity if deceleration occurred over 1 second. Even if real-world energy transfer reduced this somewhat, structural failure would be widespread. Buildings not engineered for extreme lateral acceleration would collapse. Aircraft in flight would experience sudden velocity changes relative to the air mass. Vehicles would be subjected to violent horizontal forces. Casualties would likely be highest in equatorial regions where rotational speed is greatest. Power grids would fail due to tower collapse and line damage. Water systems would be contaminated by sediment and salt water. Ports and coastal cities would face major destruction from ocean inertia. Modern food systems depend on transportation networks and refrigeration. Disruption lasting weeks could lead to shortages in urban areas. Hospitals rely on electricity, clean water, and supply chains. Widespread infrastructure damage would reduce medical capacity during peak injury periods. Satellites would continue orbiting normally, but ground infrastructure damage could interrupt communication networks. Several factors remain uncertain. How efficiently atmospheric motion would transfer into structural destruction? How much aerosol would reach high altitudes versus remaining near the surface? How much ocean energy would translate into sustained coastal flooding? Whether ecosystem tipping points would be crossed in specific regions. A 1-second pause would not permanently stop Earth's climate system, but it would inject a sudden global mechanical shock into the atmosphere, oceans, ecosystems, and human infrastructure. The long-term outcome would depend not on the pause itself, but on how much was broken during that second. Earth's rotation is constant enough that we treat it as background. It quietly shapes winds, currents, and the balance of life. We rarely notice it. Stability is often invisible until it changes. What if it did?